Imagine never having to stop at a gas station again or plugging your car into an outlet. What if the very air around us could power our vehicles? This isn't just a dream for the distant future. A Zimbabwean inventor named Maxwell Chikumbutso claims to have achieved this. He says he's built cars that run on radio frequency waves. The scientific community largely dismisses this. They say it violates the fundamental law of energy conservation. But the idea is so captivating it has sparked global curiosity. What if we could attempt our own version of this? Not a miraculous sovereignty device that's likely impossible, but a practical functional project that feels like magic. Today we re-exploring how to convert a standard car into a concept vehicle inspired by Maxwell Chikumbutso's RF-powered car. We will discuss 2 theoretical pathways. Remember, this is a thought experiment and an advanced DI electronics project. It is not a tutorial for a finished, reliable product. Safety is your absolute top priority when working with high-voltage sand-modifying vehicles. Let's be very clear about what we are not building. We're not building a free energy machine. We are not breaking the laws of physics. Radio waves carry a tiny, almost negligible amount of energy. Harvesting enough to power a multi-ton vehicle is the monumental challenge. Our goal is to create a proof of concept that can move the car short distances. We are building a mobile demonstration of RF energy harvesting. The first method we will explore is a direct RF harvesting system. This approach is the most literal interpretation of Chikumbutso's claims. The core idea is to capture ambient radio frequencies and convert them into electrical power. Think of it like a solar panel, but for radio waves instead of light. You will need a way to capture, convert, store, and then use the harvested energy. Let's start with the capture stage. You will need a wideband antenna capable of picking up a range of frequencies. AM, FM, TV broadcast, cellular signals, and Wi-Fi are all potential sources. A Disc 1 antenna or a log periodic antenna could be good choices for their wide frequency range. The antenna is the fishing net you cast into the ocean of radio waves. The next stage is the rectifier and TSYS, the heart of the system. Its job is to convert the alternating current from the antenna into direct current. This isn't a simple diode rectifier like in a power supply. We need a highly efficient circuit that can work with very low power levels. We will use a concept called a voltage multiplier like a Cockcroft Walton ladder or even Bettera specialized circuit designed for this exact purpose. This is called a radio frequency energy harvesting circuit. These are often built around specialized chips like the PowerCast P2110. These chips are engineered for maximum efficiency at low power. They can take OTNI AC signal and output a usable DC voltage. The output from this rectifier and harvesting circuit will be very weak. It might be mere millets off power. We cannot power a car with this directly. So we need a buffer, a reservoir to slowly collect this energy. This is where a high-capacity storage system comes in. We will use a bank of supercapacitors. Unlike batteries, supercapacitors can charge and discharge extremely quickly. They are perfect for absorbing small intermittent bursts of energy. You would connect the output of your harvesting circuit to the supercapacitor bank. Over time, as the car sits in an RF-rich environment, the capacitors will charge. This could take hours or even days to store a meaningful amount of energy. Once a sufficient charge is built up, we need a way to use it. We need a power management system. This system monitors the voltage of the supercapacitor bank. When it reaches a preset high threshold, it connects the capacitors to the next stage. That next stage is a DC to DC converter. This converter takes the variable voltage from the capacitors and boosts it to a stable higher voltage. For a small car, you might aim for 48 to 96 volts DC. This high-voltage DC is now ready to be converted into motion. This is where an electric motor conversion comes in. You would need to replace the car's internal combustion engine with an electric motor. A series wound DC motor is a common choice for DIY electric vehicle conversions. It's simple, robust, and easy to control. The motor is connected to the car's drivetrain. To control the motor speed, you need a motor controller. A simple high-current DC motor controller will work. You connect the output of your DC to DC converter to the input of the motor controller. The motor controller's output then goes to the electric motor. Finally, you need a throttle. A simple potentiometer or a Hall effect pedal from an e-bike can serve as the throttle. The throttle sends a signal to the motor controller telling it how much power to deliver. So, let's trace the complete energy path for Method 1. Ambient RF waves are captured by the wideband antenna. The antenna sends the AC signal to the RF energy harvesting circuit. The harvesting circuit rectifies and slightly boosts the voltage. This tiny trickle of DC power charges the supercapacitor bank very slowly. The power management system watches the supercapacitors. Once charged, it engages the DC to DC booster converter. The booster converter sends high voltage DC to the motor controller. You press the throttle and the motor controller sends power to the electric motor. The car moves forward for a very short distance until the supercapacitors are drained. Then the cycle must begin again. The performance of this system would be extremely limited. You might get a few hundred FT of movement after a full day off charging, but as a demonstration of the principle, it would be visually stunning. Now, let's move on to the second and far more practical method. Method 2, the targeted microwave power beam system. This approach is less about ambient energy and more about wireless power transmission. It's inspired by technologies like Nikola Tesla's Wardenclyffe Tower or modern laser power beaming. The concept is to have a dedicated power source that beams energy to the car. This is not free energy, it's simply moving the outlet from the wall to a transmitter. But it would allow the car to drive around without cables within a certain area. For this, we need two main components, a ground-based transmitter and a receiver on the car. Let's start with the transmitter. You would need a powerful microwave source. A magnetron from a commercial microwave oven could be a starting point, but we must modify it to work with an antenna. We need to create a directional beam of microwave energy. You would connect the magnetron to a parabolic dish antenna. This dish focuses the microwaves into a narrow powerful beam. Think of it like a spotlight, but for microwave energy instead of light. This transmitter would need its own significant power source like a generator or a large battery bank. It is not a source of energy. It is a relay. Now for the car itself, the car must be converted to electric drive. Just like in Method 1, it needs an electric motor, a motor controller, and a throttle. But the energy storage and harvesting system is completely different. On the roof of the car, you would install a rectifying antenna or a rectenna. This is a special device that combines an antenna and a rectifier circuit into one. It is designed to efficiently capture microwave energy and convert it directly to DC electricity. A rectenna array might be made of many small dipole antennas, each with its own diode. When the microwave beam hits the rectenna, it generates a DC voltage. The power from the rectenna can be quite substantial if the beam is powerful and well focused. This power can then be used in one of two ways. The first way is a direct drive system. The DC output from the rectenna is fed directly into the motor controller. As long as the car is in the beam, it has power to move. The moment it leaves the beam, the car stops. This is simple but very restrictive. The second more sophisticated way is a hybrid system. The rectenna's output is used to charge an onboard battery pack. A small lithium-ion or lead-acid battery would work. The microwave beam acts as a wireless charger for the car's battery. The car can then drive using power from the battery, not just the beam. It could drive out of the beam's range for a short time, then return to recharge. This is far more practical and allows for greater movement. A power management system on the car would switch between battery power and direct rectenna power. The major challenge with Method 2 is aiming. How do you keep the microwave beam focused on the car's rectenna as it moves? You would need a tracking system. The car could have a small radio beacon like a GPS transmitter. The ground-based transmitter would have a computer-controlled aiming system. It would use the beacon signal to constantly adjust the parabolic dish, keeping the beam locked on target. This is a complex but solvable engineering problem. The safety implications of Method 2 are immense. A powerful microwave beam is invisible but extremely dangerous. It could cause severe burns, interfere with electronics, and pose health risks. This experiment would need to be conducted in a remote-controlled environment with clear safety protocols. Never ever point a functional transmitter at people, animals, or inhabited buildings. Now, let's compare our two theoretical methods. Method 1, direct RF harvesting, is a fascinating scientific curiosity. It demonstrates a principle, but is utterly impractical for real transportation. The power levels are simply too low. It would be a great exhibit for a science fair or a tech demonstration. Method 2, the microwave power beam, is a more credible engineering concept. It has been demonstrated in laboratories for powering drones and other small devices. Scaling it up to a car is a massive challenge, but it doesn't violate known physics. It is a wireless extension cord, not a perpetual motion machine. For the aspiring inventor, which path should you consider? If you want a weekend project to learn about electronics, start with Method 1 to build a small-scale version that can power an LED from across the room, then scale it up to power a small model car. The principles are the same, just the components get bigger. If you have serious engineering resources and a safe place to experiment, Method 2 is the more rewarding challenge. Start by building the Rectenna and testing it with a stationary microwave source. Prove you can power a light bulb wirelessly. Then work on the tracking and mobility aspects. Regardless of the method, the first step is always the electric vehicle conversion. Find a small lightweight car like an old Gia Metro or a classic VW Beetle. Remove the engine, gas tank, and exhaust system. You'll need to install the electric motor and connect it to the transmission or a new drivetrain. Mount the battery pack or supercapacitor bank securely low in the chassis. Install the motor controller and connect it to the motor and the throttle pedal. This foundation is common to both of our ARF power methods. The energy source is the only thing that changes. Let's talk about the tools and skills you will need for this ambitious project. You must be proficient with electronics, soldering, reading schematics, using a multimeter, and an oscilloscope. You need mechanical skills for the car conversion, welding, machining, and automotive repair. For Method 2, you will need programming skills for the tracking system. You will need a well-ventilated workshop and a significant budget for components. Supercapacitors, high-power motor controllers, and microwave components are not cheap. This is not a project for a beginner. It requires patience, perseverance, and a deep respect for the dangers involved. So, what is the truth about Maxwell Chikumbutso's invention? Without independent, verified testing, we cannot know for sure. The laws of thermodynamics are the most tested and reliable laws in all of science. The burden of proof lies with those claiming to have overthrown them. Perhaps his technology is a very clever application of one of the methods we discussed. Maybe it uses a hidden conventional power source. The mystery is what makes it so compelling, but you don't need a mystery to have a great project. By building your own RF-inspired vehicle, you are engaging with real science. You are learning about energy harvesting, wireless power, and electric vehicles. You are standing on the shoulders of giants like Tesla, Hertz, and Faraday. You are not chasing a myth. You are building a testament to human curiosity and engineering. So be safe, be skeptical, and most importantly, be creative. The future of transportation may not be RF power. It will likely be advanced batteries, hydrogen fuel cells, or something we haven't yet imagined. But the spirit of innovation, the Dravetto try something new, is what will take us there. Your journey starts with a single step, or in this case, a single component. Gather your tools, draw your schematics, and start.